Right, so last lesson in this pack is on finding invariant points and lines. Throughout this pack, we have mentioned invariant points and lines for various transformations, but sometimes you might have to find them for non-standard transformations, non-standard matrices and stuff. We'll start off by talking about invariant points. So remember, an invariant point is a point that when you do a transformation to it, it stays the same. Okay. So for an invariant point, if you times it by the transformation matrix, M, so times matrix by xy, you end up with xy. So finding invariant points isn't too bad because you just solve these equations and you can work out some points for x and y. Okay. You should always find that the origin is an invariant point, remember, because that's the definition of a linear transformation. But there may be other invariant points as well. Sometimes you'll find lines of invariant points, which is just a straight line where all of the points on there are invariant. We'll also look at how you find invariant lines. We'll talk a bit more about those when we get onto it. That's a trickier method, but do your best to follow it and ask any questions if you're not sure. So we'll start off talking about working out invariant points. This first question here. So we've got a transformation matrix 2 minus 1 0 1 0. It says show that 5 5 is an invariant point under M. So we're going to take this matrix, multiply it by the point 5 5, and if it's an invariant point, we should get 5 5 out. With it being a show that question, I am going to show the calculations. So doing this matrix multiplication, I do the first row times the column. So 2 minus 1 times 5 5. 2 times 5 plus minus 1 times 5. And then for the second one, I do the second row times the column. So 1 times 5 plus 0 times 5. Top one, you get 10 minus 5, which gives you 5. Bottom one, you get 5 plus 0. It's 5. Therefore, 5 5 is an invariant. Okay. It then says, what can you say about the invariant points on this transformation? So that suggests that there's more than one invariant point here. So let's do it generically this time. So let's do 2 minus 1 1 0 times by the point xy. And for invariant points, we should get the same thing out. We should get xy out. So I'm going to put that equal to xy. Doing this multiplication, so I get 2x minus y, and I get x. And that's equal to xy. So just multiply it on the left to get that vector and put them equal to each other. This gives me two simultaneous equations. So I get 2x minus y equals x. And from the second one, I get x equals y. If you tidy the top one up, so that's equation 1. But add the y across and minus the x across, I also get y equals x. Okay, so remember, these are what we call consistent equations. This means that any point on the line xy, so y equals x, is an invariant point. Okay. All points y equals x are invariant. Okay, so any coordinate where the x and y are the same is an invariant point on those. I will go at the question for you underneath. So it wants you to do the same as I've done in red. There. It says determine whether it has any lines of invariant points. So this line y equals x is a line of invariant points for this one that I've just done. Right, answer this one, you end up with y equals x again. Won't always be y equals x. We get two simultaneous equations and they're both reduced down to y equals x. So they're consistent. So you've got y equals x is a line of invariant points. Example 3 wants us to show that this has no invariant points other than the origin. The origin should always be an invariant point for this stuff, but you might not have any other ones. So again, we're just going to do the same thing. So I'm going to do -4, 1, 3, -2. times by xy equals xy. Do the multiplication and set up your simultaneous equations. So I get minus 4x plus y, and I get 3x minus 2y. That's equal to xy, which gives me my two equations. So I've got equation 1 and equation 2. Let's tidy these up. So the first equation, if I add the 4x across, gives me y equals 5x. This one, if I add the 2y across, I get 3y equals 3x, which gives me y equals x for equation 2. Now, these are not the same equation this time. So what you would do is now you'd solve them simultaneously like you normally would. Okay. So if you set these equal to each other, put the y's equal to each other, you get 5x equals x. You only get a single solution this time. So if they're the same equation, you get infinite solutions along that line. This one, you're just going to get a single point. So we get x equals 0. And then obviously if y equals x, you get y equals 0. And so 0, 0 is the only invariant So hopefully invariant points is okay. I don't think that's too bad. Invariant lines, I think gets quite hard. So do your best to follow along with this stuff, but please don't worry too much about it. Do your best to wrap your head around it, but there's more important things than this. But an invariant line isn't just where all of the points go onto themselves under a transformation. It's where the points move along the same line under the transformation. So the points can move, but it has to be along the same line. So what we do is we start off by doing a similar thing. Okay, so let me do it on here. So we start off by doing the matrix times by a point xy, but no longer does that xy have to go onto itself. So we'll put that it goes onto the image of itself. So we use x dash and y dash. Okay. But the point about invariant lines is if this point xy lies on the line y equals mx plus c, x dash y dash must lie along the same line. So I can substitute these into here with into the same equation with the same gradient and the same plus c, and that should also be true. Okay, so that's how you're going to start these invariant line questions off. You're going to multiply xy by the matrix and end up with the image, and then write down two equations, y equals mx plus c and y dash equals mx dash plus. Okay. And then we're going to get a bunch of simultaneous equations and basically try and work out what m and c are. Okay. So let's do the matrix multiplication. So here I get 2x minus y, and I get minus x plus 2y. And that equals x dash y dash. And this gives me two more equations. So 2x minus y equals x dash minus x plus 2y equals y dash. So basically here, I've got four equations. X, y, x dash, y dash. I'm going to try and kind of solve these simultaneously to work out m and c. Okay. First thing I'm going to do is I'm going to get rid of the dashes. I'm going to get rid of x dash and y dash. So I'm going to substitute equations 3 and 4 into equation 2. To eliminate x dash and y dash and get it just in terms of x, y, and m and c. So y dash from equation 4 is minus x plus 2y. That goes on the left-hand side. That equals m times x dash, which from equation 3 is 2x minus y. and then I've got plus c on the end. Next, I'm going to try and get rid of y, so it's just in terms of x. So now I'm going to substitute equation 1 into this result that I've got here. Now I'm going to sub equation 1 in. You can do it all at once if you really want to. Where I've got y now, I'm replacing it with mx plus c. So I've got minus x plus 2mx plus c equals m 2x minus mx plus c plus c. Okay. I'm now going to expand it all out and collect up my x's and my other stuff. Okay. But it's a bit of a mess. But if I expand this out here, I get minus x plus 2mx plus 2c. And here, if I expand this out, so 2mx minus m squared x minus mc plus c. There's a couple of different approaches you could do here. So I'm going to collect all the x's up on both sides and equate the coefficients. You can collect them all up on one side if you want and set it equal to 0, which is the second thing. So my left-hand side, if I factorize x out, I've got 2m minus 1 and then plus c. On my right-hand side, if I factorize x out, I've got 2m minus m squared and then minus mc plus c. Okay, so I just collected up my x's and I've got my coefficients on them.
Sorry, Joel, where's the things going? Like the c's? Because like on the left-hand side it's 2c.
I've just forgotten it. It's 2c there. Is it just that one I've lost?
Yeah. Yeah.
Now I'm going to equate the coefficients of these. So if I equate these coefficients from the x coefficients, I get 2m minus 1 equals 2m minus m squared. And if I equate the constant terms, so 2c equals minus m plus c. I need to use these then to figure out some values for m and c. So if we call this one equation 5, and this one equation 6. So equation 5 is just a quadratic in m. Okay, so I can make this equal to 0 and solve it. I'm going to go down here. So m squared minus 1 equals 0 because the two m's cancel off both sides. So this gives you two solutions. M is 1 or m is minus 1. Okay. Now that I've got some values for m, I can put that into equation 6 and see what corresponding values for c I need for each of those. And then that will give me the equations of these. So I've got one equation that's got a gradient of 1 and I've got one that's gradient of minus 1. I need to see what values of c I can get to these. Okay. So if I take m equals 1 and I look at equation 6, so both of these equations 5 and 6 have to work at the end of this. So if I put in 1, I get 2c equals minus c plus c. Obviously, minus c plus c is 0. So if m is 1, the only way that this works is if c equals 0. Okay, which tells me y equals x is an invariant line. Okay, so if I've got m is 1, c equals 0, putting that into y, so then it's plus c, y equals x in invariant. So I do m equals minus 1 to equation 6. So 2c equals c plus c. Let's put minus 1 in. 2c equals c. This means 2c equals 2c. This means c can be anything. Okay. Any value of c works for this. Okay. So at the end of this, then this means that y equals minus x plus c are all invariant lines. The algebra is quite tricky in these. It's easy to get bogged down or forget what to do next. But ultimately, you're trying to get rid of x dash, y dash, and y, and then trying to work out m and c. And then again, what happens at the end, I think, is a little bit tricky. So the values that you find for m and c have to work for both of these equations, and they will tell you what types of invariant lines you've got. Have a go at the question for you, please, and I'll have a wander around your stuff. So these solutions do it slightly differently to how I do it. But ultimately, you should get the same answer. So they've got y equals x and y equals minus 2x.